last few lectures you learnt about stable matchings, right? Some techniques which is rotation, and you looked at the stable roommate algorithm, okay, and Gale-Shapley you have already seen, right? Okay. Now we will talk about the fairness in the stable matching problem. Okay. So what is unfair? Tell me, what is unfair in stable matching?
It was always one-sided. Depends on how you implement it. It is always one-sided. Have more priority and
right. So if we apply Gale-Shapley algorithm, especially if we are talking about Gale-Shapley, right? Not any other algorithm, right? This is just one algorithm. But the property of Gale-Shapley is that if you start proposals from men's side, you will get man optimal matching, right? And if you start from women's side, you will get women optimal matching, right? So this is the biasness we have. Fine. Is it really unfairness? So it is man optimal. It is towards man's side. But what is unfair here? But why? Maybe it is good enough for women also. So where is the unfairness? Right? So it's not just that if you are proposing from men's side, then we are getting men optimal matching, right? The problem is that it's worse for women, right? And if you get women optimal matching, then it is worse for men, right? So if we look at this example, it's a very small example, right? So if you look at this red matching, what is this? Is it some man optimal, woman optimal something? This is man optimal matching, right? It's very obvious because this red guy is getting first preferred partner and this green guy is also getting first preferred partner, right? So it is man optimal matching, and both the women are getting second partner, so worse, right? And if we look at this this blue matching, right, then this is women optimal matching and worse for men. Okay. This is what you would like to achieve. Why is it man optimal and worse for women, right? So we would like to have a stable matching, right, which is in some sense not a bias towards a gender, right? There are many more notions for the fairness in stable matching. So one of the notion is egalitarian stable matching, okay, and next two sessions will be focused on egalitarian stable matching, okay. What is egalitarian stable matching? Of course, we want to find a stable matching. Let's define some notations. So MR, MW, we are in the bipartite graph setting, okay. In this talk, we are in bipartite setting. So MR, MW meaning position of women W in M's preference list, okay. So just think of it like a ordered pair. If we are saying MR, MW, meaning we are talking about MR stands for men ranking, okay. The first coordinate is we are talking about men M, and W is particular woman. And W or WM is position of men M in W's preference list, okay. Okay. Now this is the notion of egalitarian matching, right? What are we trying to do? Look at the matching, right? For each pair, look at their rank, right? So we are going over, let's say mu is a matching, okay. By the way, this definition has nothing to do with stability, okay. So given a matching, I can find the egalitarian cost, okay. So for a matching so if the edge is matching edge is, let's say MW, right, then we will see that, okay, where is W in M's preference list, add it, where is M in W's preference list, add it, right. But there are some unmatched regions as well, right. So what will you do? What do you think? Okay, it's written, but yeah, what's the logic? If someone is unmatched, what should be the egalitarian cost of that particular man or woman? Basically it is unmatched, right. So size of preference list of that particular person plus 1, okay, that is the cost of being unmatched, okay. So is the definition clear for egalitarian cost?
What is the plus 1 for?
So this notation is for preference list, okay. So this, I mean, it should be bracket here, preference list plus 1.
So what is the plus one for? What are we adding the constant for?
So plus 1 just, no, it's not about constant, right? So X is, let's say, unmatched person, okay? So if X is matched with the last preferred agent in the preference list, right, then what is the ranking? Last person, right? So we want to ignore that because it is unmatched, so plus 1. Okay. So it like this plus 1 is also inside the summation, okay? Okay. So now our goal is to find a stable matching that minimizes egalitarian cost, okay? Okay, so in different papers, different books, right, it depends on how egalitarian cost is defined, okay? It is also possible that instead of you are saying MR, you can also count from the back side, right? And at that point of time, we may ask for maximizing this function, okay? But this is the standard definition, and this is what we are going to use, okay? Okay. So the first question that arises here is that indeed there is man optimal matching, there is women optimal matching, right? Even if there is something in between, okay? Of course, you learned that there are exponential many stable matchings. So there is something in between, okay? But if something in between can give me egalitarian stable matching, okay? Or maybe one of them, man optimal and women optimal, is itself egalitarian stable matching, right? That could happen, right? So let us look at this example. What is man optimal matching here? It's very simple example, you can quickly see. M1 W1 M2 W2, right? M3 W3 M4 W4, that is the man optimal matching here, okay? Okay, what is the egalitarian cost? 4. How come 4? M1 is getting first person, right? W1 is getting last person. Exactly, right? For each edge, the contribution is coming as 5, right? For M1 it's 1, for W1 it's 4. So 4 plus 1 5, and that's happening throughout. So the egalitarian cost is 20. Okay. What is women optimal matching here? Right? M1 W4, right? It's very simple. I mean, I create example like that. M1 W4, M3 W3 M4 W2 M3 and W1 M2, right? And that the cost again is 20. Okay. Now look at this stable matching. Okay. This is some stable matching, right? And if you notice, you can compute the egalitarian cost of this particular matching is 16. Okay. So basically the idea is that now for every pair, earlier the cost was 5, right? Now the contribution is 4, because 2 for M1 W2 also we have 2. Okay. So it's 16. Okay. So now at least we know that such matchings do exist. Okay. Now the question is, how do we find it, can we find it, so and so forth. Okay. Okay. So good news is that for egalitarian stable marriage problem, right, that is when we are talking about bipartite graph, then the problem admits polynomial time algorithm. Okay. And this is what we are going to see in this lecture. So the toolkit that we will use, male oriented shortlist, now you already know, right? Rotations, concept wise you understand. ST cut. How many of you know ST cut problem? I am not asking for algorithm, just the definition. Yes.
It was like we are making, there is in the graph, in a diagram graph, there is a source and a target, which is actually a flow kind of problem.
Exactly.
Now we are making two steps. The ST cut is something like whatever flow is going from, or the edge is going from S subset to the D subset in the subset which they contains.
Right. So don't worry even if you don't know or did not understand, because we'll look at the definition later when we need it. Okay. Okay. So male oriented shortlist, you know that it is you look at the W's list and remove M from W's list and W from M's list if W receives a proposal from someone she likes better than M. Okay. So here of course we are talking about the man proposal algorithm. Okay. Okay. So you looked at the lattice structure, right? So we start from an optimal matching, we can apply certain set of rotations and obtain a stable matching, right. But we are not interested in any stable matching, right. We are looking for egalitarian stable matching, right. So, we need to understand what is a good set of rotations, right, so that we get egalitarian stable match, and how do we find it efficiently. Okay, these are the two questions. Let us say mu is a stable matching and mu prime is another stable matching that we obtain by eliminating the rotation rho, something. Okay. Now, let us understand what is the difference between the egalitarian cost of these two matchings. Okay. Is it like I need to find the egalitarian cost of mu prime from scratch, or I could do something better. Okay. Okay. So, let us say this is a rotation and this is the weight of rotation. So, I will explain you in a minute why are we talking about this. If you notice as at W weight of rho, right, what does the first summation term denote basically? What does it compute? Tell me. After rotation, what is it telling me? Yes? Exactly, right. So, whoever is involved in rotation, right, we are saying that, oh well, what is the change in the value, right, because currently Mi is matched with Wi, that is why this is a pair in rotation, and after eliminating rotation it is going to be Mi Wi plus 1, right. So, Mi's partner is changed from Wi to Wi plus 1, right, and what is the change because of this? Okay. What is happening with the women, right? We apply the rotation, we started from man optimal matching. So, we know that when you apply this rotation, women partner is going to improve, right. So, Mi is the current matching age and Wi will move to Mi minus 1, right. So, what is the change in the cost because of this? Okay. Now, how many of you are able to understand that why do we have this minus here? Okay, let us look at an example to understand this. Yeah, you want to say something?
Is it because we're saying that the egalitarian value of another state is.
It's okay, it will help in recording.
Oh, sorry. Is it because we're saying that the weight of that rotation, if we remove that, then it will either be, like it will cause a significant change in the egalitarian value of mu prime will be different from the egalitarian value of mu?
Indeed, but why do we have minus and not plus, for example?
I'm assuming that the rotation before it was causing an increase in it, so doing minus would provide a better egalitarian value, hence indicating.
So the thing, okay, let's look at an example, okay? Okay, so let's say these are the preference list, okay, and this is the man optimal matching, okay. These are the short list, I mean we don't need to compute it, just believe me. So one rotation here is M1 W5, M3 W8, okay. So what happened? M1 partner changed from W5 to W8, right. So W8 partner was M3 and it moved to M1, okay. Now for M3 partner changed from W8 to W5, okay. Okay. Now you look at W5's preference list, what happened? M1 to M3, okay. So what is the change in the preference list of M1 and M3, right? The difference is 1, right, and it is increasing, right, okay. So increase meaning this will decrease your egalitarian value, right, and what is happening with women? It is increasing. For W5 it increased by 2 and for W8 it increased by 4, right. Okay. Now, when I need to compute the egalitarian cost, right, after eliminating rotation, of course, I know that except M1, M3, W5, W8, the cost is not for other agents will not change, right. Okay. So, what is cost of matching after eliminating rotation? Rho naught, whatever was the cost earlier, right, plus we increase 1 for M1, plus 1 for M3, minus 2 for W5, minus 4 for W8, right? And this is exactly what your formula is doing. Okay? Okay. Yes? Yes. So this is basically just a notation that says that you have eliminated rho naught from UM.
It's okay, fine, okay.
It's not divided by, okay? It's just a notation, yes.
When we have men optimal stable matching, it will have the maximum egalitarian value always.
Why?
Because every time men get worse partner, but women improves. So, like these two will have the maximum egalitarian value and all the intermediate
But
ones.
see, it also depends on what you call. Indeed, maybe, so you can think of that way that because it's man optimal matching, right, no man is going to get better than that partner. So for man side, you are not going to, get anything from the left side, okay, and for the women's side, you are not going to get anything from the back side. So you are right, that's a, yes. So okay, so negative actually just depends on how I compute, it depends, so because see, here the difference is positive, but in your formula if you notice, it will compute negative value, right, because we are saying this minus this, right. So that is why we have. Now it just depends how you define W rho, accordingly you will do addition or subtraction, okay. So it just depends on how you define W rho, okay. For algorithm I need this, that is why we have defined that way. Okay, so what is our goal? Our goal is to find a set of rotations of maximum weight, right? Because set of rotations of maximum weight, you delete it, you get the best optimal matching. Okay, so what could be one possible algorithm? Anything? What could be the algorithm? Something which occurred to you? So like one natural approach is that you just find a set of maybe all rotations, we can find it in polynomial time, right, in n square time. You find the weight of every rotation, this is also just polynomial time computation, okay, and then you find the rotations of all positive weight. Is it correct? Is it? How many of you say that it is correct? You did so well in quiz. Wait, just raise your hand. How many of you think that this is correct? Okay, fine. I am not talking about efficiency. I am just talking about correctness. Is it correct? Yes? Just say yes or no. It is not correct. So you are still thinking because some of you are not saying no also. How many of you think that it is not correct? 1, 2, 3, 4, 5. Okay. Why? No, but okay. So greedy doesn't work. That don't say that.
After performing one rotation, the weight of all rotations will change because there are n square rotations given a matching. Perform one rotation, you get another matching. Now again there are n square rotations possible.
Does the weight of rotation depend on matching? Does it depend on matching? What is the definition? Does it? It's just about the position. Where is your current partner and this thing. Of course it does. Yes, yes, it does. Fine. But see, when you know the rotations, right, you also know how to eliminate it, right. Accordingly, you can find the weight of all the rotations and compute these values, right. Yes or no? Right? Okay. Yeah, there's something very simple. You already did it in second lecture. Yes. Okay. So yeah, he's close to the answer. Let's see. Yes.
One more thing. We are taking all the positive weighted rotations.
Correct. Correct.
It could be that currently I just have a small negative, have a very good positive in the second, because by this rotation I created another rotation.
Okay.
Which is dependent on it.
Okay.
So by that way we cannot say that. We have to first check. Indirectly we have to check all possible matchings, not all possible
No.
rotations.
So no. Just rotation is good enough, but the wrong is that very simple. Yes.
Suppose that we need to respect that downward closure property also.
Exactly, right? You have closure property, you have precedence relation, right?
Yeah.
There are, in some sense you were trying to say that, right? And he was also trying to say that you cannot just apply rotation, like any rotation at any point of time. There is precedence relation, there is closure property, okay? So this algorithm is not correct, okay? Okay. So we just don't want, so this is not actually our goal. Our goal is to find a closed set of rotations of maximum weight. Okay, this closed set was missing earlier in our previous goal. Okay. Okay. So now what the toolkits we are going to use. So Sushmita told you about rotation digraph in the morning, right? And she told you that we can sparsify that graph, right? Because in rotation digraph we know that the number of vertices is
Linear, right.
n square, right? Number of rotations is n square, so number of vertices is n square, but edges could be many more. We didn't say anything about that, right? But we will sparsify it, okay? And even that will be n square now, okay? And we will construct that graph. I'll tell you how to construct that graph, and then we will construct an instance of ST cut, okay? I'll define what is ST cut, and then using an ST cut of this new graph, we will find the closed set of rotations of maximum weight. Okay? Okay. So let us understand this. Vertex set is again same as earlier, set of all rotations. Okay? Okay. But we don't have all the edges here. We are defining weighted rotation diagram, right? So weight of a vertex is same as the weight of the corresponding rotation. Okay? Okay. Now you add edge if two conditions. MW is in rotation, right? But why is it in rotation? Because someone else moved M to W. Okay? MW is in the rotation. What does this mean? This means that this is a matching edge at this point of time, right? But why is it a matching edge? Maybe because of some other rotation. Okay, you eliminated some rotation, and that is how you move, like M is moved to W. Okay, so in that case you will add edge from rho prime to rho, and this is obvious, right? Because what are we trying to say? Rho prime has to be predecessor of rho, right? Because rho prime is the rotation that brings M to W. Okay. Okay. Next is rho moves M below W. MW is not a matching edge here. But something magic happened that M moved below W, okay? And why it happened? Because in some other rotation, rho prime, W moves above M, W's partner moves above M, okay? So let us see how that, so these are called type 1 and type 2 edges, okay? So let us understand how this will happen. So this is a set of rotations, and these are the weights, okay? So we'll call it as a negative node if the weight is negative, otherwise positive node. Okay. Let's look at this short list. So this is a rotation rho naught, like these are the rotations. Okay. Now just for you to remember what is the construction of our edges. Okay. Okay. Now if I look at M1 and W8, what rho naught did? Rho naught moves M to W8. Okay. And M1 W8 is an edge in rho 1, right? M1 W8 is in rotation rho 1, right? So we will have edge, we will have which edge? Come on. Come on. Which edge? What happened? M1 W8 is, look at your edge description, right? Rho 1, M1 W8 is part of rho 1, correct? And rho naught did what? Move M1 to W8. So edge is rho naught to rho 1. Okay? This is type 1 edge. Okay? look at what rho 1 is doing for M2. For M2, if you notice, when you eliminate, what is happening? M2 moves below W8, right? Because what is happening? If you eliminate rho 1, M2 will be matched to W6, right, which is below W8, okay? Okay. But why it happened? See, next person in the short list is W8, but we are saying no, well, what rho 1 is doing? Move it to W6 and below W8. Why is it happening? Because something happened with W8, right? W8 is not even there, right? So, what happened? It moved to W6. Why? Because what happened in rho 0, for W8 it moved from M3 to M1. So, when you eliminate rho 0, W8 is not there even in M2's preference list, okay, because rho 0 moved W8 to M1, okay. So, this is the type 2 edge. So, you can notice here that there can be both the type of edges between the two rotations, two vertices, okay. So, now you can verify, if you want to click picture you can, okay, and just for record, and we will anyway share slides. Okay. Now, the construction is clear, I hope, of weighted rotation diagram, sparse diagram. Is that clear? Okay. Now, look at the ST cut. What is ST cut? Input is a directed graph G, okay, a capacity function on every edge and two special vertices S and T. Okay. Now, question is, does there exist a partition of VG into A and B such that S is in A, T is in B, and then look at the capacity of the edges going from A to B, okay. That is what we need to minimize, okay. Okay. So, this is the ST cut problem. How many of you have seen this problem? How many of you have done DAR course? Design and analysis of algorithm? Exactly. Okay. So, fine, just believe me that this is solvable in polynomial time, okay. Okay. So, how will we construct now ST cut instance given the weighted rotation diagram, okay. So, the vertex set is same as rotation diagram and we have additionally two vertices S and T, okay. So, basically we are now going to construct the super graph of this, okay. Vertex set is there, the whole edge set is also there, okay. Now, but it is unweighted, okay. We do not have weight on the vertices, we are constructing an instance of ST cut, okay. So, it should satisfy the definition of ST cut, right, my input instance, okay. Now, look at the negative weight nodes. You draw edge from S to all those negative nodes, okay. If you notice left hand side, rho 0, rho 1, rho 3, rho 4, these are negative nodes, okay. So, from S I add edge to all these nodes, okay. Now, there is only one positive node, rho 2. So, from positive nodes we add arc to T, that is all. This is the construction, okay. So, you take the rotation diagram, vertex set, edge set, copy everything in ST cut, add two vertices S and T, from S add arcs to negative nodes and from positive nodes you add arc to T, okay. What more I need to define in this graph? This is ST cut instance, right. We have directed graph, we have S, we have T, what more? Capacity of edges, right, okay. So, for all the original edges, the capacity is infinity, okay. From S to whatever arc you have added, the weight is absolute value of the weight of rotations, okay. That is all. Now, we have complete instance of ST cut, okay. Okay. Now, we want to find maximum weight closed subset of G using ST cut in my newly constructed graph G prime. Okay. So, this is the these are the steps that we are going to do. So, K is let us say some minimum ST cut in G prime which I can find in polynomial time, okay. Now, look at the positive nodes of G prime, right, whose edges are not in K, okay. whose edges are not in K. What does it mean basically? These positive nodes are in the which set? Set containing S or T? Positive, right? This PK set, what are we saying? We know that from every positive node we have arc to T. Okay? Okay? So PK, this is only basically the positive nodes which are in the same set that contains T. Okay? If other for the other positive nodes, you will have arc. Okay? Okay. But we need to worry about closed set, right? So what do? You take PK and all the nodes, right, that reach to a vertex in PK in G prime. Okay? Let us understand using example. Okay? So let us say this is your ST cut instance, okay, and let us say this is some cut. We are not talking about minimum or what, okay, we are just trying to understand the algorithm for now. So this is the cut AB. Where are the edges? From S you have rho naught, okay, from rho naught you have rho 1, but will this edge contribute in cut, rho naught rho 1? No. Rho 3 rho 2, sorry rho 2 rho 3, this will also not contribute, right, because the contribution is only from for the edges that are going from A to B. Okay. We have rho 2 to rho 4, it will not contribute. So the cut here is 1, right, value of the cut is 1. Now what is my PK, tell me? All the definitions are here. What is PK? What is PK? Set of positive nodes of G prime, okay, positive nodes, okay. See, nodes do not have weights, but that is a different thing, right. I just gave them name, something is negative node, something is positive node, okay. How many positive nodes do you have in G prime? 1, okay, which is rho 2. Okay. Now set of positive nodes of G prime whose edge into T are not in K. Rho 2 to T edge, is it in K? K is cut? No, right? So PK is rho 2. Is that clear to everybody? This example is very simple because there is only one positive node. Okay? Okay. Now if you look at this, right? What are we saying? PK and all nodes that reach to a vertex in PK. Which vertex is that? Rho naught, correct? Rho 2 is my PK, and if you look at rho naught, rho 2, rho naught is the only vertex, right? If you look at the graph there. So this is the, like algorithm says that this is the maximum weight closed subset of rotations. Okay? This is what our algorithm is saying. We do not know if it is correct, okay, but these are the steps that are written. Now do you understand the algorithm? Let us first talk about that. Is the algorithm clear to everybody? Huh? Correct, right. So basically you need to check that what all vertex has path to rho 2, right. So do you have a path from rho naught? No. Do you have, sorry, rho naught you have, rho 1, rho 3, rho 4, okay. Okay. Why is the algorithm correct? These are the just steps which I told you, right? Right. So we now need to prove that the minimum cut that you find in G prime is equal to the maximum weight rotation, closed set of rotations in original graph G, right? Agree? All of you? Okay. Let us make some observations, okay. So let us say Q is your maximum weight closed subset of G. The first observation is, if there is any negative node in Q, right, it is there because it precedes at least one positive node. Otherwise, why will you do this rotation? right? As these people were saying earlier, right? Why are you doing this negative rotation? The only reason is in future you are going to do positive rotation, which you cannot do without this negative rotation, right? Is that okay with everybody? Okay. So let us say P is set of all positive nodes in G, and S is a subset of P, and it's a look at n minus S meaning its neighborhood intersection with the negative nodes. Okay. Now our goal is to find a subset of P, right, positive nodes that maximizes weight of S minus weight of negative neighborhood of S. Okay. Okay. Look at the now this thing. Do you buy this, that maximizing the above set is same as minimizing the set WP minus this, right? WP is the total possible value for the positive nodes, right? Now you subtract it. Now this is the value you want to minimize, right? It's same as maximizing that value. Okay. So now I can say that my goal is to find a subset that minimizes this value, correct? So you see how are we changing as per our convenience, what is doable, right? We had some goal, then we are just looking at what like if we can reduce to something you know, easy to solve. Okay. Okay. So this is equivalent to that I want to find a subset of P that minimizes WP minus S plus weight of this, like we just solved the above equation. Okay. Okay. So now to like I told you that our how will we find it? We will find the minimum ST cut, and that is how we will give the maximum weight closed set of rotations, right. So this is the thing that we need to prove, that minimum ST cut is same as this value. Agree? Okay. So let us do that. Okay. Now to show such kind of equalities, right, one standard technique is, it's an equation, right, A is equal to B, right. So how can I prove it? If I just show that A is less than equal to B and A is greater than equal to B, then I know that A is equal to B, and this is exactly what we are going to do. Okay. Okay. So let us consider minimum ST cut of G prime, A star, B star. Okay. Let us look at the picture. It's a ST cut, so of course I will have S in A star and T in B star. Okay. Okay. Let us say these are some set of positive nodes. Okay. It could be empty, we are not saying anything. We are just saying look at it, whatever is the set of positive nodes, call it S star. Okay. Okay. These are the remaining vertices which will be in A star. Okay. Now where is n minus S star? This we need to ask ourselves. We are trying to look at the decomposition of graph now, right. So n minus S star, where is it? Can it be in A star? Can it be in A star? Just try to relate that what is the capacity of these, like if this happens, right, then what is the capacity of cut? If this happens, what is the capacity of cut? See, there are real edges between n minus S star and S star, do you agree? Right, these are the edges in G, right. What is the weight capacity of the edges which are in G? Infinity, correct. So if I have this edge, then my ST cut value is going to be infinity, right. But what is the value of min ST cut? In this particular problem, do I know that we have finite cut? We do know, right, because you put everything in A star and put T in B star, that is a valid partition, right. And what is the cost? What is the capacity cut value? Whatever it is, but it is some finite value, right? Right, because the edges that are going across are the only edges that are from positive nodes to T, right, which is the weight of rotation, and weight of rotation is not infinity, it is some finite value, right. Okay. So n minus S star cannot be here, it has to be in B star. Okay. So what is the contribution? You will have such arcs, right, which will have contribution in the cut value, agree, and from S to this value. correct? Because from S we added arcs to all negative nodes, right? Okay. So what do we know? That cut of A star B star, I do not know what, there might be other edges which are contributing, I do not care, okay. But these are the edges that are definitely contributing, right. So I know that cut of A star B star is greater than or equal to this value, agree? Because what are we counting here? These arcs, right. What is the capacity of these arcs? Weight of these vertices, right. And what else? These arcs, right. These are the weight of the nodes in n minus S star, right. Okay. So cut value is greater than or equal to Wp minus S star plus this value, right. So I can say that this is definitely greater than or equal to whatever minimum is achieved, agree. So what did we show? Did we make any progress towards our goal? Half meaning? Exactly, okay, by half he means that one direction we have proved, right, this is what you mean, okay. We want to show minimum ST cut of G prime is this, A star B star is a minimum ST cut and we have proved that this value is greater than or equal to this, right. Now we need to show less than or equal to, correct, okay. Now this is what we want to show, okay. So what should be my approach? So we started with earlier a ST cut, right. Now what can we do? You start with a set of positive nodes, okay. Let us say this. This is like, now we are trying to construct a partition, okay. So we have, of course we need to put S in A, T in B, okay. Now this S you put in B side, okay. Okay. You put neighborhood of, negative neighborhood of this set in B, okay. Remaining negative nodes you put in A, okay. And remaining positive nodes also you put in A, okay. Whatever is remaining that you put in A, okay. Okay. Now what are the contributions? You have S arcs from S to n minus S and you have arc from P minus S to T, right. These are the only arcs that are going from A to B, okay. Now because of this, what can I say? This is some cut whose value is this much, right. So what is the value of min cut then? Definitely less than or equal to this, right, because there is some cut who has this value, right. So minimum is going to be only less than, right, or the same value. So cut of A star B star is this value, right. Now if you notice, I could say this for any set S, right, because given the set of positive nodes we constructed this cut, right. So I can say that this is also less than or equal to this value. Is it clear to everybody? Are we done? Are we done? How many of you think yes? Are we done or not? Come on, what is our goal? Our goal was to show equality. In the previous slide we proved greater than or equal to. This slide we proved less than or equal to. So we are done, right? Okay. So we have proved it. Okay, and this is exactly what we want to prove, that minimum ST cut is equal to minimum of this thing, right. If you notice, this is what we reduced to, right. Okay. So, and it is not just that we are giving the statement that these two values are equal, but given the minimum ST cut you can even find it, right. This is what we see in the previous previous slide, right, that you had ST cut, minimum ST cut, and you given that you can compute a closed set of rotations, right. This is our algorithm. Okay. Now what about running time? So what are our major steps in this algorithm? We constructed a sparse rotation digraph, then we constructed an instance of ST cut, and then we solved min ST cut problem. Okay. So what is the time for sparse rotation digraph construction? it is n square. Okay. Yes, rotation diagram. Okay, because if you notice every pair is part of only, so right. Okay, as instance of ST cut also we can just construct in n square time, right, because you just copy G first to G prime and then you just added S and T and added some arcs. Okay, so this all is again linear in the input size, and this input size itself is n square here. Okay. Okay. Now you just find ST cut, whatever best algorithm is known, we do not care. Okay, that is going to give you the algorithm. Okay. Okay. Any questions here? All good? Okay. So next, like we'll take a break, right? Okay, I finished early, so we have now 40 minutes break. Okay. So after that, we will see how to find egalitarian stable matching in general graphs. Okay. Okay. Let's stop here.